Hello everyone, welcome to the Multi Virtual. Hope you are doing good. Today I'm going to continue with chapter number 4, that is processor architecture. In the yesterday's class I have finished only one topic. In yesterday's class I have started with the chapter number 4, that is processor architecture. Today I'm going to continue with the same chapter, that is chapter number 4, that is processor architecture. So let's take a quick review of the yesterday's class, what we have covered in the yesterday's class. Yesterday was in the yesterday's class we have discussed about the architecture or the processor architecture. Means what do you mean by processor architecture? So whenever we say architecture, the word architecture refers to the building design and the construction. So whenever we design something, whenever we build any building, whenever we design any building, that is known as architecture. In the computer terms, architecture means the designing of the computer system. If I'm talking about the desktop, so it is a designing of the desktop. If I'm talking about the laptop, it is a designing of the laptop. So in computers, it is a design, it is the architecture of the computer system. Computer architecture is a broad topic that includes everything from the relationship between multiple computers. So whenever multiple computers connect with each other, that is known as, or that is done by the processor architecture, and that term is known as client server architecture or client server model to specify or to specific or to identify specific components inside a computer. Then we also talked about multiple processor architecture like Intel, IA32, X64. There are multiple processors that are used for implementation of processor architecture. So this is the most important type of hardware design is a computer's processor architecture. The design determines what software can run on the computer and what hardware are supported. So it designs or it supports or it depicts or determines what kind of software are involved or what kind of software are used for building the software and what type of hardware are used for supporting the software. For example, Intel X86 processor architecture is the standard architecture used by the most PCs or used by mostly PCs. Then note that most modern computers have 64-bit processors and chipset. Means the day-to-day modern computers or the day-to-day computers have 64-bit processors. But the earlier computers uses 32-bit processors. There is a difference between the 64 and 32. Then we also discuss about the instruction set architecture, that is ISA. So how I can define or how I can give multiple architecture, multiple designing, that is your instruction set architecture. There are two parts. One is compiler OS application program, one is CPU design, circuit design and the chip layer. So it consists of two parts, one is above, one is below. Above indicates how program or how the computer executes the program, while the below part indicates how multiple instructions will execute simultaneously. Then we also talked about the Y86 processor states. Then we also talked about the instruction sets like hold, NOP, CMove, IR move, RM move, MR move, OP1 that is operation, JXS, call, return, push 1, pop 1. Then Y86 instruction format, that contains 1 to 6 bytes of information that is read from or read from the memory. Then these are the set 2, that is hold, NOP, call, JXX, RET. Then this is the set 3. The main difference is that this contains multiple instructions for jumping. These are the multiple instructions or multiple commands or the multiple registers for jumping. And these are the multiple registers for operation, that is AND or add, sub, XOR. Means arithmetic as well as the logical operations. Then we also talked about some move operations or the move registers like RR move 1, C move LE, C move 1. Then we also talked about the encoding registers. Means what are the encoding registers used in IA32 and X86-64. This is the instruction example. This is the addition instruction. This is a generic form. That is add 1 RA RB. This is register A and register B. This is the general form or the generic form. This is your encoded representation. That is how this instruction will stored in the registers or will stored in the memory. This is add values in register RA to that in register RB. Store the result in register RB. Note that Y86 only allows addition to be applied to the register data. Means they cannot apply the addition to the memory or the memory content, but it applies the addition to only the register, that is RA and RB. Then next point or multiple points are used for the encoding purpose like ADL, EAX, EXI. Then we also talked about some arithmetic and logical operations that we use in processor architecture, that is instruction code, function code, add, subtract, and XOR. And subtract are arithmetic operations, XOR and are logical operations. Then we also talked about some move operations, how move will be done in the processor architecture. So we can move the operations from register to register, from immediate means variable to register, from register to memory, and vice versa from memory to register. These are the multiple instructions for move instructions. These are the some conditional move instructions, that is how conditionally we move from one part to the another or from one location to the another. This is RR move 1 AB, RR move 2 RB, then C move 1, C move 1, C move E. This is move when less or equal, move unconditionally, move when less. Next is your jump instruction, that how we are jumping or how we jump from one location to another location unconditionally and conditionally. So there are multiple jump operations. One is jump unconditionally, jump when less or equal, jump when less, jump when equal, jump when not equal, and so on till jump when greater. Then next is your Y86 program stack. So this is the stack operation, that is how stack will be maintained. This is stack bottom and this is stack top. How stack will be maintained from the top to the bottom, how data will be stored from the top to the bottom. Then next is your stack operations. We have also studied what are the stack operations that will be used in the Y86 architecture. So multiple stack operations are used like push, pop. Push means adding the values, pop means retrieving the values. So there are two types, basically two types of operation. One is push and another one is pop. Push means inserting and pop means removing. Then we also talked about how we call or how we use the subroutine call and the return. Means how our main program is divided into multiple parts, that is subroutine, and how subroutines are called and how subroutines are returned by the functions. So returned by the subroutine values. Then there is a miscellaneous instructions like NOP, that is not used for anything. Hold for stopping the execution, that is done by the stop executing the instructions. Then we also talked about the status conditions, means what are the status conditions that is used in Y86 architecture. There are multiple mnemonics and the code used for status conditions like HLT, ADR, INS, AOK. Then we also talked about how to write the Y86 code, that is how we are writing or how we are able to write the Y86 code in processor architecture. So the first target is that write the code in the C language, then compile for IA32, then translate it to the Y86. So first of all, the first target is writing the code in C language, C programming language, then compile for IA32, then translate into the Y86. This is a coding example. This is Y86 code generation example 2. This is your first example. This is second example. First try, write typical array code. So first of all, write the coding, C language, then compile with the help of GCC, and then define the problem, gives the output. Then we also talked about two instruction set, that is CISC and RISC. CISC means Complex Instruction Set Computer, and RISC means Reduced Instruction Set Computer. These are the two instructions that are used with Y86 instruction. This is stack oriented instruction set. This uses stack to pass the argument to save the program counter, and uses push and the pop operation for performing the value, for performing the operations. There are condition codes, there are philosophy, arithmetic instructions. Then RISC, that is Reduced Instruction Set Computer. So that's all for yesterday's class. Now let's start with the today's session, that is next topic, HCL. Next topic is your logic design and the HCL. This says in hardware design, electronic circuits. Electronic circuit means with the help of which we can perform the operations by sending the signals. That is, electronic circuits are used to compute functions on bits and to store bits in different kinds of memory elements. So in hardware design means whenever we design the hardware, or whenever we design anything in computer, electronic circuits are used. Electronic circuits are generally used to compute functions on bits. Means how to compute? By using the electronic circuit to compute the functions on bits and to store the bit in different types of memory elements. Most contemporary circuit technology represents different bit values as high or low voltage on signal wires. In current technology, logic value 1 is represented by high voltage. So 1 is represented by the high voltage and 0 is represented by the low voltage. This is 1 of around 1.0 volt, while the logic 0 is represented by the low voltage of around 0.0 volt. So 1 is represented by 1 is true and it is represented by high voltage of around 1.0, and 0 is represented by low voltage of around 0.0. Three major components are required. One is combinational logic, then memory element, then clock signals. Three elements are required in logic design. In this section, we will give a brief introduction, brief description of these different elements, components. We will also introduce HCL, that is Hardware Control Language. The language that we use to describe the control logic of different processor design, means how the flow of the computer works. That is designed, or that is shown by the HCL, that is Hardware Control Language. We only describe HCL informally here. A complete reference can be found in web SI/HCL. So in this chapter or in this topic, it is defined very formally or informally. That is not to the mark. That is only the introduction. That is your HCL. But if you want to take any opinion, give any opinion, so use another verb, that is ARCH HCL. Now, first one is your logic gates. Now, let's see with the help of PPTs. Digital logic design. First of all, meaning of the logic design. It is a system in electrical and computer engineering that uses simple number values to produce input and output operations. So it is a simple and the electrical system that is used in computer engineering that uses simple number values or uses a minimum or the simple values to produce input and output operation. Suppose I am giving two input and the output are 4, that is done by the logic design. Suppose I am giving only one input and the output is only 1, that is also done by the logic design. So whenever we perform any operations by giving the input and taking the output, that is done or that is known as the logic design. That is also known as digital logic design. Next point says, as a digital design engineer, you may assist in developing cell phones, computers, and related personal electronic devices. Continue reading to find out what training it develops skills in function algorithm and binary conversion. School offering computer science degrees can also found in these popular choices. So it is very important to know the logic design. What is the logic design? How we can implement the logic design? Because this is very important. If you have a personal equipment like cell phones, computers, any personal notepad, anything personal that is an electronic device, and if you have a knowledge of logic design, that is what is the logic design, how we can build the logic design. So it is very easy to cope up, or it is very easy to handle all the personal electronic items. Now, next is your Boolean algebra. What is the Boolean algebra? That is, when we talk about in terms of zeros and ones, that is known as the Boolean algebra. Means performing the algebra. Algebra means mathematical calculations, arithmetic operations. So whenever we perform arithmetic operations on the Boolean values means zeros and ones. So if I combine both these, so whenever we perform the operations on the zeros and ones, that is known as Boolean algebra. This has two values, either 0 and 1, and it has three basic functions, means the three important functions, that is AND, or NOT. So we are using, or we can use three basic functions, that is AND operation, or the AND function, or function and NOT function. Next is, any Boolean function can be constructed, from these three. Means any Boolean function or any Boolean expression can be represented or can be constructed from these three items or these three functions, that is AND, or NOT. Then these are the multiple tables. This is the AND operation. As I told you earlier, AND operation is whenever we perform the AND operation, that means multiplication. If both the values are true, then only output is true, otherwise the output is false. If only one value is true, then the output is false in AND operation, because that AND indicates multiplication. So this is 0, 1, 0, 0, 0, 0, 1, 1. This is the output. These are the input and these are the output. This is the logical OR operations. In this, if any one output is true, that is 1, then if any one input is true, then the output is 1. Means there is no boundation on the inputs. If any one input, like if I am using 3 bits, 1, 0, 0, only one, that is only one bit is true, that is 1, then the output is also true. NOT operation, that is the inverse, 0 becomes 1 and the 1 becomes 0. Next is your algebraic laws. There are multiple laws that are used in Boolean algebra. Like in mathematics, we use various formula. In the same way, we use various laws that are used for algebraic operations. First one is your identity. A1 equals to 1A equals to A. So if I multiply A into 1, that is also equals to 1 into A, and that is also equals to simple A. And if I add 0 to the A, that is equals to the 0 plus A or A, because 0 has no value, and multiply by 1, it gives the same value. So it gives the same, that is A. Then next is your dominance. A0 equals to 0A equals to 0. Next, 1 plus A equals to A plus 1 equals to 1. Commutative law or commutative law, A plus B equals to B plus A. And when we multiply AB, that is equals to B into A. Then associativity law, A into BC is also equals to A into B and then C. So either I multiply B into C then multiplied by A, or either I use AB then multiplied by C. Then next is A plus bracket B plus C, or that is also equals to A plus B. This is A plus B, and then adding the A plus B value to the C. In the same way, another law is distributive law. AB plus C, that is distributed into two parts, AB plus AC. A plus BC is divided into two parts, A plus B into A plus C. So whenever I take A common, that becomes A plus BC. Then next one is your De Morgan's law. This is very important law, that is A plus B complement. In this there is an OR operation that becomes, or that converts into the AND operation, that is A complement into B complement. Means I am using the plus sign, that is OR operation, that is converted into the multiplication, that is AND operation, that is A plus B complement is equals to A complement into B complement. In the same way, whenever we use AND operation, that is whenever we use multiply, that is converted into the addition or the OR operation, that is A into B complement equals to A complement plus B complement. Means in De Morgan's law, plus is converted into multiply and multiplication is converted into plus. This says addition represents 0, as I told you. Multiplication represents AND, as I told you. Note is represented by prime A dash, this is a complement, or an over bar, that is A bar. So I can denote the note by either, this is note, either A bar, that is bar. Examples, this is a note, A note BC, A plus, that is OR operation, A into B note into C plus A B C note, A note B note C note. This is another example, A into B plus B into C plus A into C plus A B C. So these are used for multiplication. All the values are multiplied with each other and then add the values one by one of the all values. These are the multiple symbols that is used in the logical operations like AND or NOT. This is the AND operation. This is the OR operation. This is a symbol for AND. This is a symbol for OR. This is a symbol for NOT. So in OR there is a rectangle type, then there is an oval shape. In OR this is the shape of the oval, and NOT there is a circle at the end. That is a NOT. Now let's see with the help of some PPTs, that is most important PPTs. This says topics of this slide set, means what are the topics covered. To execute a program, we need communication, computation, memory. So for executing a program, we need generally three things. For one is communication, next one is your computation, next one is your memory. Everything is expressed in terms of bits, that is either zeros and ones, and that requires communication, low or high bit, voltage, computation, compute Boolean algebra, storage, or the store bits. Now next is your digital signals, means how digital signals or how bits are carried over to the digital signal or via digital signals. So this is the digital signals, and bits are transferred from one location to another location with the help of digital signals. This says use voltage threshold to extract discrete values from a continuous signal. Work with live for communication. Next says it has a simplest version, that is 1 bit signal. It can be either high range, that is 1, or it can be either low range, that is 0. It has two values. Either it takes high range or either it takes low range. So either it takes 1 or either it takes 0. Not strongly affected by noise or low quality elements. It is not affected by the low quality elements or the noise. It is simply used and simple to use and the fast to access. These are the truth table for AND operation. What are the truth table? Combination of zeros and ones, that is known as the truth table. So this is the truth table for AND. That is represented by the AND operation, that is A and B. As I told you, this is the AND operation used for multiplication. So this is AND A and B, that is equals to 1. When means the output is 1 when both A equals to 1 and B equals to 1. As I told you, it gives the value or it gives the output true whenever A is 1 as well as the B is 1. Otherwise it gives always the error, or otherwise it gives always the false result or the wrong result. That is, if A and B are 1, then only it gives the output, otherwise it gives the 0, that is your false condition. Then next is your this is your logic gate. This is 0 1 AND operation. Then 0 0, the output is 0. Means there are no there is no 1 or both the values are not ones. That is why the output is 0. 0 1, only one input is 1, other input is 0, so the output is 0. Third, 1 0, in the same way, only one input is 1, other input is 0, so the output is 0. Last one, 1 1. In this, both the inputs are ones, so the output is also 1. This is 1 1 1. Then OR operation or the OR table, that is A bar B. This is denoted by AND, this is denoted by the 5 bar. A bar B equals to 1 means it becomes 1 when either, as I told you, when either A equals to 1 or B equals to 1. I mean, there is no hard and fast rule that any both the inputs are 1. No, either A equals to 1 or B equals to 1. This is your 0 0. Here there is no input, that is 1, so the output is automatically false, that is 0. Here 1 0 1, at least one input is true, so the output is true, that is 1. Whenever I say true, so this means when true is denoted by 1 and the false is denoted by 0. Then 1 0, at least one input is true but other is false, that is the output is true. In this, both the inputs are true, so the output is also true. So in AND, both the inputs are true, then only the output is true. In OR, at least one of the input is true, then the output is true. Then there is a NOT operation, that is A not equals to 1 when A equals to 0. That means reversing or inverting the bits. So 0 becomes 1 and the 1 becomes 0. Then XOR operation, that is A complement B equals to 1 when either A equals to 1 or B equals to 1, but not the both. This is 0 1 1. So this says this gives the output 1 when either A equals to 1 or B equals to 1. This is the same as this one, but not the both. Means both, if both are 1, then the output is true. This is reverse of the AND operation. This is the condition. Addition of the OR operation. Otherwise it's same, but the addition is that it gives the output 0 whenever both the inputs are 1. And otherwise, if there is only one input, that is 1, then the output is 1. So this is 0 0, there is no input 1, there is not both the inputs as 1, so the output is 0. In this, at least one input is 1, so the output is 1. At least one input is 1, output is 1. Here both the inputs are 1, so the output is 0. Then these are the logic gates. How to compute with logic gates? So how are these logic functions actually computed in hardware? This says how. That is, logic gates are constructed from transistors. The output is a Boolean function of input. So these are the input and this is the output. The gate responds continuously to changes in input with a small delay. So this is your AND operation, this is your OR operation, this is your NAND symbol, this is your NOR symbol, this is NOR, this is XOR. You see, the OR and the XOR are same, but only one line is different, that is this one. Otherwise, every symbol is also same. Here there are two inputs, that is A and B, and the output is only one, that is C in every symbol. This says, how many of these do you really need? It is pretty easy to use only three functions, only three Boolean functions, that is AND, or NOT. So it is essential, or it is easy to cope up with the only three Boolean functions, that is AND, or NOT. These are the multiple operations, that is, now this is the output, or this is the value. First of all, A naught, this is A naught, then there is a pi, another pi, means operating the OR operation, B and C. So this is the AND operation of B and C. As I told you, the symbol, this is AND and this is OR. So first of all, and NOT is denoted by using the circle. So first of all, this is A naught, then OR, this is done by the OR. First of all, take B and C. This is the AND operation. Now, performing the OR between this A naught and the B and C. So this is A naught, this is B and C. Now, performing the OR operation by using the symbol, by using the gate. This is the OR gate, and the output is J. So this is A, B, C, D, E, J. These are the multiple variables. You can use any type of variable. A, B, C, D, E, J. So this is how we can represent the symbol. So first of all, take the values like A naught, then OR operation, B and C, means performing the AND operation, and then performing the OR operation among the A complement and the B and C. These are the values 0 0 0 1 0 0 1 1 0 1 0 1 0 1 1 1 1 1 1 is also 1. Next is your combinational circuit. Combinational circuit means there are n inputs, so there are m outputs. Means if there are 10 inputs, then the outputs are also 10. If there are 3 inputs, then output also 3. So the same the number of inputs, the same the number of outputs. The box contains a acyclic network of logic gates continuously respond to change in input. Output becomes Boolean function of the input. So this is used for this output, this arrow is used for this output, and so on. There are 4 arrows, and the 4 arrows are used for input and 4 arrows are used for output in this example. The following circuit, this is known as circuit, generates a 1 if A and B are equal. So first of all, take A and B, this is A and B, then performing the NOT operation of A, NOT operation of B, then again find the AND operation, and then A and B and the A naught and B naught B, performing the OR operation. So first of all uses A and B. This is A and this is B. This is B. This line is B. Let's see. Yeah. This is A. This is B. Right. So performing the AND operation over here. Then use A node. This is your A node. Here line comes. This is your A node. Then B node. This is your B node. Again performing the AND operation on the A node and the B node. This is A and B. This is A node and B node. Now performing the OR operation. This is the OR operation. Now performing the OR operation. Putting the line. Filling the line. This is also a line. Then performing the OR operation and then gives the. This is the way how we can represent the Boolean expression with the help of logical circuit. Means first of all performing the operations or performing the logic gate that is used inside the bracket and then used that is outside the bracket, means performing the AND operation or the OR operation. Then next part is your HCL. HCL means hardware control language. It is very simple hardware description language. Boolean operations have syntax similar to the C logical operations. So this is very simple hardware description language, and this is very simple language as similar to the C logical operations. We will use it to describe control logic for processors. This is same hardware description languages, that is Verilog, VHDL, that describes control data movement. So hardware description language defines the control as well as the data movement. Next, compile a hardware description into the logic. So HDL is used for compiling the hardware description into the circuit, means form the circuit by using the commands or by using the equations. Then next is HCL is a subset of the control description. So subset means the similar version of the control description, that is your HCL. Next, what are the data types used in HCL? One is bool, that is boolean, A, B, C, normal variables, int for use for words, A, B, C, normal variable, does not specify word choice. In the same way, we are using or we have to use different statements in boolean in HCL, that is bool A equals to bool expression, int A equals to int expression. These are the HCL operations. What are the operations? AND, OR, NOT. Word comparison, this is used for comparison. Double equals to, not equals to, less than, means these are the logical operations. Less than equals to, greater than equals to, greater than. Then this is the set membership, that is finding the A in B, C or D. Then these are the word expressions. These are their case expressions like A colon A, B colon B, C colon C. In the same way, we evaluate Boolean expressions A, B, C in sequence. In the same way, return the corresponding word expression for the successful Boolean evaluation. These are the word equality, that is how we can check the word equality. This is the example. Then this is also an example how we can perform the operations. This is minimum of 3 words, that is combinational circuit, as I told you. Now, constructing an ALU. ALU is arithmetic and logical unit. These are multiple functions like add, subtract, XOR, AND, NOT, and other. There are combination logic to perform functions in ALU. Multiple combinational logic. Combinational logic matlab means AND or NOT. There are multiple control signals to select the function to be performed. There are multiple instances of the 1-bit ALU. The following is a 1-bit adder. This is the adder. This is C in and S C out. These are adding a pair of 4-bit input. These are the inputs C in, C out, sum using the 1-bit adder. Next is your flip-flops. Now let's see one more slide. As I told you, multiple operations. Now let's see with the help of slides. These are the multiple basic logical symbols that are used in combinational circuit. This is exclusive OR, that is XOR. As I told you, there is a same symbol of the OR but only one line is added. And the condition is that whenever both the inputs are 1, then only the output is 0, otherwise the output is true, that is 1. These are additional logic operations like NAND, AND operation, that is performing the AND or inverting the AND operation, that is known as NAND, that is not of AND. This is not of OR. That's why it is using bubble or the circle at the end. That is no, not of OR. Means first of all finding the OR operation and then inverting the bits of the output, that is known as OR. In the same way, performing the AND operation and inverting the bits are known as NAND. Then there is a buffer, there is a XNOR operation. I mean, first of all finding the NOR operation and then finding the XOR for the NOR operation. These are some basics. Now let's see in your book. Logic gates, as I discussed, there are generally or there are standard 3 types of Boolean functions like AND, or NOT. These are used for AND. This is double ampersand is used for and double pipe is used for OR, and NOT is used for exclamation mark. Like this one. AND, NOT, and OR. Then we have these instead of bit level C operators like this one, this one, this one. There are multiple C operators also like AND, or NOT, but we are using double AND, double ampersand, double pipe, and NOT operation. Logic gates are always active, means it is always active, it cannot be deactivated. These are the logic gates types. This is AND, this is OR, this is NOT. There are 2 inputs A and B and the output is only 1. There are 2 inputs and the output is 1. There is only 1 input and there is only 1 output. These are the symbols, that is double ampersand, double pipe, NOT of A. This is the combinational circuit. This is the combinational circuit and the HCL Boolean expressions. This is by assembling a number of logic gates into a network, we can construct computational blocks known as combinational circuit. As I told you, combinational circuit means there are n inputs, so there are n outputs. So whatever the number of inputs, then the same number of output is also there. This is the output of 2 or more logic gates cannot be connected together, otherwise the 2 would try to drive the wire in opposite directions, possibly causing an invalid voltage or a circuit malfunction. This is the next example. In this, first of all finding the A and B, then means denoting the first of all AND operation of A and B, then denoting the AND operation of A naught and B naught, and then finding the OR operation between these 2 values. Now there is an example that is known as multiplexer. This is multiplexer. This is the same example. Next is your word level combinational circuits and HCL integer expressions. This is your bit level, this is your bit level or the bit equal, and there is a word level. There is a word level multiplexer circuit. This is the word level multiplexer circuit. This is used for simple S. This is used for S note. These are the AND operation, and this is the OR operation. This is the bit level. This is the word level. These are the select statement as we use in the C language. This is the case expression. Same. These are the same values which I have discussed with the help of PPTs. Now, this is a four-way multiplexer. So, multiplexer is a concept in which we are able to give n number of inputs, but the output is only one. So, if there are 5 inputs, then the output is only one. That is known as multiplexer. So, if I define multiplexer, means combining multiple inputs but gives only one output. So, for example, I am using 5 inputs, then the output is only 1. So, n number of inputs, but the output is only 1. Now, next is your set membership that I will take after 5 to 10 minutes break. Let's take 5 to 10 minutes break and then come back, start with the next topic, that is set membership. And again, going to the next topic, there are flip-flops, loops, and so on in the combinational circuit. So first of all, take 5 to 10 minutes break. Next topic is your set membership. So let's start with next topic, that is set membership. This side, in our processor designs, we will find many examples where we want to compare one signal against a number of multiple signals that I described you or I explained you earlier, multiplexer and the demultiplexer. So this is, there are multiple conditions, there are multiple scenarios where we have to compare one signal against a number of possible matching signals. So there is only one output, but there are so many, or there are multiple possible matching signals. So such as to test whether the code for some instruction being processed matches some category of instruction code. As a simple example, suppose we want to generate the signal S1 and S0 for the four-way multiplexer. So this is the signals. There are 4 inputs, that is A, B, C, D, and there is only the one output. This is control, that is used for controlling. There are 2 signal lines, that is S0 and S1 for the four-way multiplexer of figure 14. This is the four-way multiplexer by selecting the high and the low order bits from a 2-bit signal code as follows. This is S0, this is S1, this is multiplexer. There are 4 inputs and there is only one output. This is, in this circuit, the 2-bit signal code would then control the selection among the 4 data words. There are 4 data words. These are the 2 control signals. 4 data words are A, B, C, D. We can express the generation of signal 0 and S0 using equality test based on the possible value of code. So this is your Boolean expression. S1 equals to code double equals to 2. There is a OR operator, code equals to 3. So S1 contains either code 2, either code 3. S0 contains either code 1, either code 3. The general form is this one, I expression, in I expression 1, I expression 2 till I expression k. So there are multiple expressions and we have to test, we have to take the general form, and the general form is that I expression, that is EXPR, in I expression 1, I expression 2 till I expression k. Then next is your memory and clocking, that is how different memory and how different clock signals are used in combinational circuit or in logical design. This says combinational circuits by their very nature, do not store any information. Instead, they simply react to the signal at their input, generating output equals to some function of the input. So this meaning of this is that combinational circuit do not store any information, but they behave like a signal at their input, generates the output that is equals to the function of the inputs. To create the sequential circuit, that is, that have state and perform computation on that state, we must introduce devices that store information represented as bits. So whenever we use or whenever we want to create a sequential circuit that is used for representing or that are represented by the bits. Our storage devices are also controlled by single clock. These are the clock registers, that is only registers, these are the random access memories. These are the multiple states like X, Y, Z. These are the errors, read operations, write operations, data memory, data out, clock signals, address, data in. Now let's see with the help of PPTs. Note this one, right. So now next is your flip-flop. So flip-flop are also the combination of inputs and output that are used to store the bits. There is a table that you have to see what are the table, what are the inputs and what are the outputs. So this is a table, this is SR, as the name advises, SR flip-flop. This is the inputs are two, that is one is S, another one is R. There are two inputs, 0, 0, and the output is Q, that is action is hold state. Then 0, 1, the Q next is 0 and the action is reset, means reset the values. 1, 0, the output is Q and then the action is set, that is set the values. 1, 1, there is no operation, that is X, that is not allowed. Next is your gated D latch, that is D latch flip-flop. First one is your higher level representation. Then these are the circuits. This is the D latch truth table. This is EC 0 XQQ. There is a knock change. 1 0 0 1 reset. 1 1 1 0, that is equals to set. And this is your representation, that is D Q CP Q dash. Next is your 4-bit register that are used for 4D latches. All shares the E, AKA, WE or write enable input. These are the D0, D1, D2, D3, CP. D0 to D3 are the data input, Q0 to Q3 are the outputs. Then next is your register file abstraction that requires or that provides the CPU with temporary and fast storage access. Then raise through condition with D latches. So there is a raise condition that is used with the D latches, that is used by the combinational circuit. Then next one is your H triggered flip-flop. So one is your SR flip-flop, D flip-flop, latch flip-flop. Next one is your H triggered flip-flop. This changes conditions or this changing the state means either 0 or 1, either at the positive edge or at the negative edge. So in H trigger flip-flop, the output can be changed at the positive edge or at the negative edge. A register is made up of several flip-flops, each providing storage and access for an individual bit. A register file is made up of several registers and control logic. Next, clock. As I told you, clock means carry out or increasing the signal from one place to the another. Like in a day-to-day life, clock means whenever we see the timing that jump from one location to another, from one part to another, that is known as clock. In the same way, whenever we have to control the timing control the timing for our signals in architecture, in processor architecture, that is known as controlling, that is known as clocking. So this says it is an integral part of every synchronous communication. There are two types of communication, or there are two types of system. One is synchronous, another one is asynchronous. That is, A is used along with the synchronous. In synchronous communication, there is a synchronization between the sender and the receiver. Means sender and the receiver are using the same concept. Both are mutually connected with each other. But in asynchronous, both the sender and the receivers are not mutually connected with each other. They are using the separate computers. And how they are knowing that one is sending the data and another one is also sending the data? By using the concept that is known as start and stop. For example, suppose A and B are asynchronized, that is not synchronized with each other. A wants to send the 5 bits to the B. So A adds one extra bit that is 0 along with the 5 bits. So that data becomes 5 to the 6 bits. And at the end, that is 0 is inserted, A inserts the 0 at the beginning and inserts the 1 at the end. So A adds 2 extra bits. So whenever there is a 5 bits or whenever there is a 6 bit register, 2 more bits are added, that becomes 2 extra bits. If 5, then 2 extra bits, that is 7. If 7, 2 extra bits, that is 9. If 6, 2 extra bits, that is 8. So one is known as the starting bit and another one is known as the ending bit or the stop bit. If I say start, then stop bit. If I say starting, then there is a ending bit. So the most general term used is start bit. So if the start bit is 0, then the stop bit is 1. So it is mandatory to use the start bit as a 0 and the stop bit as the 1. So A transfers the data by using the start and the stop bit, and it is going to the B. B recognizes the data. Yes, this is coming from one receiver because there is no synchronization. How he or she knows, how B knows? By using the synchronization, by using the concept of the start and the stop bit. If B sees, then there is a start bit. Yeah, that is sent by some receiver or that is sent by some sender. And if there is a stop bit, that is 1, so that B also know that the data will finish or data is finished. So 0 represents the starting and the 1 represents the ending. So that is known as asynchronous, but in synchronous, all the signals, all the computers, all the persons are interacting with each other and they are mutually connected with each other. That's why we use the clocking in the synchronous communication. That's why it is written. It is an integral part of the synchronous system. Because for synchronization, we need the timing, we need the clocking, we need the clock for the timing. That is your integral part of every synchronous system. Next point says can be global. Global means clock can be used at any time, at any place, anywhere, at any from any point of person or from any person. So that is global, that is used by any person at any time. There is no foundation that there are authorized user, there are unauthorized user. No, that is common, that is global to everyone. Next, this is the diagram. This is your clock period, clock width, falling edge, rising edge, clock width. Next, clock frequency equals to 1 divided by clock period. This is the formula how we calculate the frequency by using the 1 divided by clock period. Then 1 kilohertz, that is measured in cycles per second, that is hertz, that is 1 kilohertz equals to 1000 cycles upon a second. That is 1000 cycle divided by second. Then 1 ns, that is nanosecond, equals to 10 power minus 9 seconds, that is equals to 1 gigahertz, that is 10 power 9 clock frequency. Then next point says higher frequency means faster speed. As you know, if there is a higher frequency, that means a faster speed, and that is provided by the clock that is used in combinational circuit or logical design. Next is your random access memory that stores many words or that is used for storing the words. conceptually a large array where each row is uniquely addressable. So random access memory is a large array, or it is a large storage area where each row is uniquely addressable or uniquely identified or fetched by using the concept of the memory, or by using the concept of the address. Next point says, in reality, much more complex to increase throughput. That is, in reality, it is used, or RAM is used to increase much more complex systems, to increase the throughput or increase the output. Then next point is, multiple chips and banks interleave with multi-word operations. So multiple chips and multiple operations and the multiple banks interleave or uses the multi-word operations while using the RAM. There are multiple types of implementation for RAM. One is dynamic RAM, next one is a static RAM. So there are two types of RAM, dynamic and static. One is your DRAM, that is your dynamic RAM, that is a large, inexpensive but relatively slow. So it is a large memory, it is a cheaper memory, that is inexpensive. But the main limitation is that it is relatively slow. One transistor and one capacitor per bit. Reads are destructive, require periodic refresh. So it requires day-to-day basis or monthly basis or the weekly basis refreshment. That is, it requires periodic basis refreshment. That is, on a period wise, there is a refreshment that is done in the dynamic RAM or the RAM. Then next point says, access time takes hundreds of CPU cycles. If I want to access something with the help of dynamic RAM, so it uses or it takes hundreds of or so many hundreds of CPU cycles. Next is your static RAM. It is very fast, but it is expensive. It is large, inexpensive, but slow. But static RAM is fast as well as the expensive. So this is the advantage. It is fast, but the limitation is that it is expensive. Static RAM requires 6 transistors per bit. Then second point says streaming orientation. So there are two types of RAM, dynamic RAM and static RAM. Now, what is the summary? The summary is, first of all, computation that is performed by the combinational logic. Then it implement means logical design implements Boolean function. Then it continuously reacts to the input. For example, multiplexor, it reacts to the input whenever we give multiple input, then only always the output is only one. Then next is your storage, that is how we can store the data. It is stored in the registers, that is a part of the CPU. This says register holds a single word. It is used for temporary result, that is used for temporary location, temporary result, not used for permanent result. Then loaded on the rising clock. Means the clock is carried on, a clock is waiting for the receiver. Whenever the user receives the input, a clock is updated. So it is like a watch. Whenever you insert something, a clock will increment. Whenever you delete something, a clock will increment. So it is loaded on the rising clock. Then next is this, memory is much larger. So memory is much larger, that is memory requires lots of computation. There is a huge memory that is used for storage purpose. Then next point says variety of implementation techniques. So there are multiple implementation techniques that is used for storing the data, like dynamic RAM, ROM, primary memory, secondary memory, hard disk, floppy disk, and so on. Now let's take some examples. This is also the wind up stage. Now let's take some examples. if I have to perform the AND operation, right? So if there is a number 101 and I have to add the values, so performing the add operation, as I told you, AND is your not plus, this is your multiply, right? So if I want to use the AND operation, 1 1, as I told you, whenever both the inputs are 1, then only the output is 1. Here both the inputs are 1, then the output is 1. Here 0 1, only one input is true, but the other input is false, so the output is false. Here both the inputs are true, then the output is true, that is 1 0 1. So the output is 1 0 1. In the same way, if I have to perform or if I have to give the OR operation of this one or the AND operation, let's say example, like this one. So first of all, find the AND operation, 0 and 0. Both the inputs are 0, then the output is 0. Here at least one input is true, but other input is false, so the output is false. If both the inputs are true, then only the output is true. This is 0, this is 0, this is 0. So output is 0 0 0 1 0 0. This is your AND operation, that is denoted by multiply. Now next is your OR operation, that is denoted by pipe. You can use double pipe or single pipe. This means whenever there is only one input that is true, or whenever only one input is true, other input is false, then only the output is true. If both the inputs are true, then the output is true. But if both the inputs are false, then the output is false. So if there is only one input that is true, then always, or then it's okay, then the output is true. Suppose this is 1 0 1 1. 1 0 0 1. Here both the inputs are true, then the output is true. Here at least one input is true, then the output is true. Here both the inputs are not true, that is false, so the output is false. Here 1 1 is, so the output is my 1 0 1 1. In the same way, let's take another example. Here 1 and 1, output is 1, output is 0, output is 1, output is 1. So the 1 1 0 1, this is done by the OR operation, and the symbol used for OR operation is this one. This is your OR operation. In the same way, if I have to define the AND operation, that is your AND operation. Next is your NOT operation, that is used for inverting the bits, and this is denoted by exclamation mark. Suppose I have a number this one. So the NOT operation is 0 1 0 0, means inverting the bits. 1 becomes 0, 0 becomes 1, 1 becomes 0, 0 becomes 1. This is the NOT operation for the 1 0 1. Right. In the same way, suppose these are the numbers. So the NOT operation is 1 0 1 1 1. So the NOT operation is this one, and that is denoted by this, using this one, and then there is a circle. This is a NOT operation, right? Now let's do some circuits so that you can understand. Suppose this is my input A and B, or A naught, B naught, there is the AND operation also, then there is the AND operation of A. This is my equation. So first of all, using the values, that is A and B, A naught or B naught A. So using only two symbols, that is A and B. First of all, finding the AND of the A and B. If I am doing this one, so this is the AND of A and B. I have written A dot B, that I have written A dot B, that is A into B. Then A naught into A naught or B naught. So first of all, draw the A node. This is your A node and this is your B node. So first of all, finding the OR operation. This is your OR operation, so use this symbol. So this is your A node or B node. Right. Now next is your first then finding the OR operation of this one, of both the values. This is this value, this is this value. Then find the OR operation. This is your OR operation. Find the OR operation of this value. Right. Then next is AND A, means finding the A. Now take the value, this is A. Now finding the AND operation of this and this. Now using the AND operation, that is denoted by this one. This is like this one, and then this is the AND operation. This is the way how we calculate. So taking at least two values or the two numbers, that is this one and this one, finding the operation, then use that next one and then finding the operation with the variable. So this is the way how we can represent the sequential diagram. I am taking another example, simple example. Suppose the A or B into, that is AND only B, or B node and A node. Right, for example. So first of all, take A and B. So take A or B, two variables. First of all, find the OR operation. So find the OR operation. This is A and A or B. Right. Then using the AND of A. So take this one, find the AND operation. This is the AND operation. Find the AND operation. Now these two are solved. Now using B node and A node. So first of all, find A node. In the same way, find B node. In the same way, find B node. This is the A node and B node. Finding the AND operation. This is A node and B node. Right. Now using the OR operator. Use the OR operator. Now use the OR operator. So this is your diagram. So this is the way we can represent the diagram. Use only two equations first of all, then finding the operation, and then use the third variable or the third operation, then finding the operation. So you take either these and this one. You can take either this and this one, or you can take this and this one, or you can take this and this one. Means randomly you pick any functions, you can randomly pick any equation, find the operation, and then finding with the next operation. That is the way how we can draw the sequential circuit. And this is clear to you. So I think that's all for today's session. There is no other slide. Yeah, I've taken this one. Yeah, that's all for today's session. Now, if you have any doubts, then please text the doubt and I will answer you. I've taken that topic, that is logical design. But before giving the doubts, let's take a quick review what we have covered in the today's class. In today's class, I've taken the chapter, or I've taken the topic, that is your digital logic design and the HCL. This is the main topic, that is how we are designing and how we design the computer system with the logic. That is your logical design or digital logical design. This is digital logic design is a system in electrical and computer engineering that uses simple numbers values to produce input and output operations. So whenever we use ones and zeros, binary number, hexadecimal number, that is represented in the computer system by the concept known as digital logic design. As a digital design engineer, you may assist in developing cell phones. For example, if you are using these designs, or if you have knowledge of these designs, these are used in the personal usage also. Then we have studied about the Boolean algebra. What are the Boolean algebra? What are the value stores? Then we have taken up or we have discussed about the different laws that is available in Boolean algebra like identity, dominance, commutative, associativity, distributive, and the most important is De Morgan's law. Means the plus becomes into and the into becomes plus. That is AND operation becomes the OR operation and the OR operation becomes the AND operation. Then we also talked about some Boolean expressions like AND, OR, NOT. These are the multiple examples. These are the logical symbols that are used for AND, that are used for OR, and that are used for NOT. This is AND, this is OR, and this is NOT. Then this is your exclusive OR. That is your next function. That is XOR. That is your exclusive OR. The main condition is that whenever both the inputs are 1, whenever both the inputs are true, then the output is false. So this is 1, 1, so the output is false. These are the additional logic symbols. These are the NAND, that is not of AND. This is NOT, not of OR. Buffer, this is used for buffer. This is XNOT, that is finding the XOR of the NOR gate. So thank you so much everyone. Now if you have any doubt, then please text the doubt and I will answer it. So that's all for today's session. In tomorrow's session I will take next topic, that is your sequential Y86 implementation. This is this topic I will show you. This is sequential Y86 implementation. So that's all for today's session. If you have any doubt, then please text the doubt, and thank you so much everyone. Bye bye.